Hello and welcome back to chemistry. This is Mrs. Schroeder. Today we're going to talk about acids and bases. So what is an acid, what is a base, and also we're going to talk about what is this thing called pH. That's a little bit of chapter 5 of the second section in 15. In 1890, a Swedish chemist named Svante Arrhenius proposed a definition for an acid. He said an acid could be any substance when added to water increases the hydronium concentration. Hydronium being this H3O+. Example of that, when I put HCl in water, it forms H3O+ and chlorine minus. So this is called our Arrhenius acid. Anything that increases the concentration of H3O+. He also defined a base as any substance that added to water generates the hydroxide ion. Hydroxide is the OH minus ion. Example, when I put sodium hydroxide in water, it dissociates into Na plus and OH minus. So this would be an example of a base. Very common acid, common bases that we use today. Some acids do generate more than one hydronium ion in water. So we refer to these as this term called diprotic, di meaning 2, or triprotic, meaning 3. For example, sulfuric acid, because it's got a 2, it's H2. When it dissociates into water, the first hydrogen comes off into H3O+, and I still have a hydrogen left. So it dissociates again to make H3O+ and SO4 2-. So it forms 2, therefore it's diprotic. The Arrhenius definition was limited, though. It wasn't a good definition for all species of acids. For example, he said it has to dissociate in water, but HCl is an acid whether it is dissolved in water as an aqueous solution or whether it is a gas, which it would be in this pure form. He also couldn't classify substances that can act as an acid or a base depending on the situation they're in. The biggest concern was I have this ammonia ion, or this ammonia molecule. When it is put in water, it forms ammonium, but there's no OH minus that comes from it directly. It eventually makes the OH minus, but not directly from the NH3+, like the sodium hydroxide did. So we can't classify it as bases, but the way it acts, we know it is a base. So in 1923, this is 40 years later before they came up with a better definition, Bronsted-Lowry, two different chemists working, I think, different in separate places, came up with another definition. They said an acid will donate a proton being an H+. Because there's only one proton, there's no neutrons, the electrons are gone, therefore it's just one proton. We represent that as an H+. And a base can accept the proton. So this is the Bronsted-Lowry definition. It's a definition we still use today. Examples. When HCl dissolves in water, there's really two steps to it. The HCl first dissolves into H+ and Cl-, then the H+ reacts with water to form my hydronium ion. It's therefore a proton donor because of this H+. Ammonia, on the other hand, is a proton acceptor because when it dissolves in water, it takes one of these protons. One of these is transferred to the ammonia, and I'm left with OH minus. So I still get my hydroxide ion, which is my basic ion, but it didn't come directly from the ammonia. It came from water. Yet ammonia is considered a base because it's a proton acceptor. It took this extra proton away from water to form the base. With the Bronsted-Lowry definition, we can also define a conjugate acid and a conjugate base. Since an acid is anything that donates a proton and a base is anything that accepts a proton, when I have an equilibrium set up, I have acids and bases on both sides of the reaction. So the conjugate acid would be conjugate acid would be the base with the proton added to it. The conjugate base, if you see this, is the acid with a proton removed from it. We call this an acid-base pair, a conjugate acid-base pair, when we work with our reaction. Some species can act as either an acid or a base, depending on if they're going to donate or accept a proton. They're called amphoteric. Water is amphoteric because we saw it could accept a proton to make H3O+, or it can donate a proton to make OH-. It depends on the situation and what it's in the water with, or what's in the water with it. In class, we'll work on how to identify these conjugate acid-base pairs. So water is an acid or base. It does self-ionize. It is amphoteric. But even without anything else in the water, there is some hydronium and some hydroxide ions present, because water will react with other water molecules to form hydronium and hydroxide. Even pure water will contain these ions. The number would be equal if I have pure water. So when I have, when I measure the concentration of the OH3 of the hydronium in a solution, I call that the solution's acidity. If it has a high acidity, it has high H3O+ ions in it. If I measure the OH-, it's called as basicity. The OH leads to it becoming a base. pH is used to measure in an easier way to talk about things. pH will measure the hydronium ions, the H3O+. So I have a scale here that goes from 0 to 14. Pure 7 is pure water. Shouldn't write over that. So 7 is our water, and that would be considered neutral. Anything below 7, this way, is an acid. The lower the number, the stronger the acid. Battery acid you don't want to mess with. This is very strong. Things that are in this range from apple juice, these are considered weaker acids. Same thing on the other side. These are your bases, anything above 7. Your stronger bases, drain cleaner, can burn your skin as badly as battery acid could. Things that are closer down here are considered your weaker bases. So anything above 7 is basic, anything below 7 is an acid. And we can use indicators when we're using any kind of solutions in chemistry. We can use indicators to tell what the pH is, because some indicators change different colors depending on the different pH that's around. For example, litmus paper turns blue with bases and red with acids. So if I put a blue litmus paper into a solution and it stays blue, it's a base. If it turns pink, it's acidic, pH less than 7. We're going to use this commonly in class. We're going to use it in the lab. It turns different shades from this red-orange color for an acid to a deep blue if it's a base. So again, blue for base, same as litmus paper. I also have things that I can put in, that I can drop in. For instance, thiamol blue will turn yellow in solutions whose pH is between 3 and 8. It turns blue in solutions whose pH is 10 or above, so yellow to blue. We've got phenolphthalein turns from clear to pink. Methyl red, which we saw before, turns from a kind of pinkish red to a yellowish color depending on the pH. So these are going to be used, we're going to use these in lab with our neutralizations, with our titrations to help us find out when the pH changes. And that's all for today. So make sure you understand the definitions of Arrhenius acid and Bronsted-Lowry acid. We'll talk about conjugate acids and bases and how to figure out conjugate acid-base pairs when we get to class. And also be aware of the pH and what the scale from 0 to 14 stands for.